Hello, Physics 2 people. In this video, I want to describe how to calculate the self-inductance of a toroidal solenoid. So just a reminder, the definition of inductance is going to be, or is the self-inductance, is going to be the magnetic flux this configuration generates by its own current. So you divide by its own current, so it's the self-inductance as opposed to a mutual inductance where it's the flux coming from another current. We've already talked about how to find the magnetic field in such a toroidal solenoid. The field lines will run in the body of this loop, and they're going to run in closed loops like that. And if you think about it, if you grab the wire inside the body, they're going to run in that fashion. So from the side, I would have magnetic field lines which go into the board or into the torus and then out over here. So we need to do that. I can use Ampere's law to find a formula for the magnetic field in the body, and I would find the integral of B dot ds around the loop equals mu naught times the current that crosses that soap bubble spanned by that loop. Well, okay, so that's pretty easy because that's just N times the current in each wire. So I get B times 2 pi r, because that arc length was a circle, equals mu naught in I. So therefore the magnetic field on the inside is simply mu naught in I over 2 pi r. Okay, and that's inside the body of the torus or toroidal solenoid. We need to next calculate the magnetic flux. Just as with the infinite cylinder, I can think of the magnetic flux as rather than having to handle some sort of weird kind of slanted 2D surface that spirals through the solenoid, I can just say that the flux through all N turns is just N times the flux through one turn. And to do that, I can simply focus on a turn that wraps around this rectangular cross section. So it has height h. It runs from RA to RB. Looking at my picture, it runs from RA to RB, has height h. And I have magnetic field lines, let's say, which come into your eye here. And to find the magnetic flux through one turn, that's going to be the integral of the magnetic field dotted with dA. Well, that's going to simply be, because they point in the same direction, so the dot product doesn't do anything. And for dA, I can simply write that as h times dr. So I'm breaking this up into little rectangles of height h and of width dr. And b is simply given by the previous formula that we found. So I could say that is mu naught in I over 2 pi r times h dr. And this equals mu naught in I, where n is the number of turns, divided by 2 pi times h times the log of RB for RA. Very good. That's the flux through one turn. The flux through in terms is going to be n times that. So the flux through in turns, let's put that over here, is simply going to be mu naught n squared h 2 pi times log of RB over RA times I. And if I divide by the current, so saying that the self-inductance is the flux through all turns over the current, that simply gives me mu naught n squared h 2 pi times the natural log of RB over RA. And that's the formula for the self-inductance of a toroidal solenoid. All right. In the next video, I will show how to calculate the mutual inductance for a configuration. It's pretty simple. And then we will also talk about transformers.